So welcome to our first session, session 1, Composites, the Greener Alternative. My name is Roberto Lopez-Anido. I'm professor here at the University of Maine and member of the Advanced Structures and Composite Center. I conduct research in the Transportation Infrastructure Durability Center and lead the area of materials. My job today is introduce our two speakers. And for that reason, I prepared a short number of slides that will bring us to the topic that they will mostly address based on their experience and knowledge. Next one. You have the clicker. Oh, I have the clicker. Again, should stay here. The title, Composites, that's what we're going to talk. In particular, we're going to talk about polymer composites, and the focus will be green aspects that show composites as the greener alternative. We're going to discuss latest composite material applications, emphasizing life cycle analysis. So our session, we have an hour and 15 minutes. We have time for questions. And I will start introducing gate to grave life cycle stages of polymer composites in infrastructure. Well, first, let's look at some examples. And we heard this morning, Professor Bill Davids talk about the G-beam girders. This is a good example of tech transfer, technology developed at the university in collaboration with Maine DOT and AIT, a partner, industrial partner, made possible the implementation of the technology in a number of bridges. Here we see the G-beams being installed in the grist mill bridge close to here in Hampden, Maine. Another application I'm going to bring is the bendable thermoplastic composite rebar for concrete reinforcement. And you may have seen these bars on your table. We have made some of them. And one of the very unique features about this type of composite rebar, in addition to be non-corrosive, lightweight, very competitive in cost due to an automated and optimized manufacturing process, is that it can be bent. And I'm going to use what appears to be a mug, but it's actually a device for bending the bar, okay? That's our little secret. I mean, that's why we have it here. Now, another application, again, of composites, and I'm going to use these applications to showcase how we go through the life cycle assessment. The third one is outlet diffusers for highway culvert rehabilitation. This is a technology actually developed by Maine DOT, the concept of the culvert diffusers. We did a small implementation in Maine with the help of Dale Peabody and staff from the hydraulics a group at Maine DOT, and this caught the attention of other DOTs, and we had a project actually installed in Exeter, New Hampshire a year ago. We are monitoring this project. We have witness panels. We need to go this month actually to do a 1-year inspection of that application. I mean, this is a product, again, of polymer composites where the manufacturing method applied here was large format 3D printing, or we call it additive manufacturing. The common theme is steel-free infrastructure. That's what we are trying to attain. So to have a big perspective on the life phases of the applications, I'm going to start with this circle that is kind of our guiding roadmap. We start with the design phase. We go through manufacturing and fabrication phase. The three products that I showed to you have different manufacturing technologies. They're all using polymer composites. In some cases, long continuous reinforcement. In other cases, short reinforcement that can be placed in different directions. Different types of polymer systems. They can be what we call thermosets or thermoplastics. Thermoplastics are the ones like, for example, the rebar that can be heated and bended or can go through a secondary forming process. And after manufacturing, we go into the use phase. My focus today will be the use phase. And what happens during this phase, and what happens at the end of the life. So how we navigate from 3 to 4 in this circle. And there are challenges during the use phase. And some of the challenges are that we don't know the longevity of these materials when they are in an exterior environment subjected to temperature, moisture, UV radiation, freeze-thaw cycles, can be exposure to chemicals, alkaline solutions when they're in contact with concrete, salt when they're in contact with de-icing chemicals, or in a marine environment. The durability response is affected also by the way these materials are made, typically a layer structure. And basically, when we go into how we design with these materials, we'll need to be able to account for that environmental response through material capacity reduction factors. So a take-home message here is that the service life assessment of these polymer composite materials is needed. Ongoing research is actually tackling this. I mean, we're looking at how we characterize the environmental exposure, how they affect mechanical properties of these materials, and we implement what we call, again, material property retention factors to account for the exposure effects in such a way that structural engineers can actually design structural components and parts. Any material characterization has this big PMTR plan to get all the properties that we need. And in a nutshell, their physical properties. We look, for example, at molecular weight changes. We look at density. There are thermal properties. Glass transition is a very important one. It dictates when the material will undergo changes, becoming softer when temperature is increased. And those are very important to determine what are the operational temperatures. Mechanical properties are key. Tensile strength, for example, is an important one. Rheological properties are needed to understand how we can process these materials. And we say that what we're going to discuss in this introduction is gate to grave, how we collect and generate data during the use phase. That's what I mean. And how we assess durability. We conduct accelerated weathering tests in the lab, and we also monitor bridges at the sites. We develop a database, and we look at both bio-based and synthetic polymer composites. I mean, we're interested in considering both, and at the end of the service life, how we recycle the materials. And this bullet list is our call for action. I mean, this is the work that we have started, the work that we are proposing to our partners. Monitor existing polymer composite installations in bridges and transportation structures to determine damage, can be delaminations, can be cracking, evaluate reduction in mechanical properties of composites using accelerated weathering lab tests, and also witness panels that are placed at bridge sites. So we need to correlate both. We correlate these results, and through that, we arrive at a comprehensive, rational approach for lifetime prediction of polymer composite materials. We need to evaluate the service life, the maintenance needs, and basically come up with a cycle assessment from gate. Gate is when we manufacture, when we produce materials, to grave, when we arrive at the end of life. I'm going to give here a brief opening to a talk that will be followed by Joe Fox. We are complementing our work with what the Trade Association, the American Composites Manufacturers Association, and the Institute for Advanced Composites Manufacturing are doing. They have a joint effort looking at life cycle assessment, and they're going from the cradle, from the stage one. Remember my circle? They're doing the 4 stages from cradle to gate. And what we're doing are, remember, stages 3 and 4, I mean, the end part of this, but we need to put them together. And this is needed to develop what is called environmental product declarations and product category rules. We're going to learn more about this with our next speaker, Reed Miller. Is going to tell us exactly what these terms mean. But the point here is the work we are doing during the assessment of the service life of this structure is not done in isolation. It's part of a bigger effort. It's part of a life cycle assessment.